Good morning, everybody, and welcome to the Target 2035 webinar today. My name is Milka Kostic, and I will be the moderator of what is a fantastic webinar. We have 2 hours with you today, and our agenda is packed with talks about different resources that people interested in chemical probes can and should be using. So the whole webinar will be structured in 10-minute sections with 20 minutes focused on just chemical probes portal. At that point, we will also pause to take a couple of questions about the portal specifically. Then we'll go on for into the second section of talks and wrap up with a panel discussion at the end. Just as a reminder, the webinar is being recorded. You can ask your questions using a Q&A feature in the Zoom, and you can ask your questions at any time during the presentations. The webinars will be available online for viewing, usually within the next week or so. And there will be a questionnaire for all the attendees to fill out at the end of the event. And that's really useful for the organizers to hear from you about what you're interested in so that we can plan future webinars. So without any further ado, I will stop sharing the screen and hand things over to Cheryl Aerosmith, who will update us on where things are with Target 2035.
Hello, everyone. It is my pleasure to give you an update now on where we are with the Target 2035 initiative. It was about a year ago, 2 years, it was 2 years ago that we first published the notion or the concept of Target 2035 and in this paper in Drug Discovery Today and some follow-up comments on the paper. So again, just a quick recap, it's an open science global movement. It's a partnership with between industry, academia, and not-for-profit. And the global vision is to develop a pharmacological modulator for every protein by the year 2035. It's open science. It's meant for the global community to share data, collaborate, and towards this goal, which is seemingly right now probably out of reach, but for various reasons, as you'll hear today, and as you've seen on the webinars over the last year, we think it could be feasible. And again, the rationale for this is that so much of the human genome and proteome is unexplored, unexplained, yet strongly linked to disease in some way. So unbiased omics studies have linked almost every protein in the proteome to disease in some way. Yet very few of them have been studied in detail, and there are even fewer pharmacological modulators of each target protein. And pharmacological modulators are amongst the most useful tools for biological discovery in general and drug discovery in particular. So we want to generate free, unencumbered, high-quality tools for the entire proteome. So what do those tools look like? Chemical probes and biological probes are the top two objectives. Chemical probes for intracellular proteins and probably mostly biological probes or chemical probes that need not be cellular penetrant for cell surface and secreted proteins. Chemogenomics libraries and what we call protein handle compounds are going to be very useful tools on the way to the most selective compounds. With the advent of proximity pharmacology methods such as targeted protein degradation, having a ligand to a protein of interest then enables one to modulate it through bifunctional compounds derived from that protein handle. So these are both key areas of interest and that we will use in Target 2035. We're now 2 years or so into the program. This launch phase that we're in the middle of is meant to establish a roadmap for coordinating international efforts by generating chemical probes, collecting, characterizing, and distributing them, developing the infrastructure to facilitate the data collection, the curation, and dissemination and mining of the data. And this is what we're going to hear about primarily today. There's some wonderful resources that are laying the groundwork for this. And to create also the sort of laboratory and physical facilities to streamline and improve ligand discovery of future targets. And then we're hoping that by the year 2025, we will be in a position to really put down the gas pedal and go full speed ahead with some of the newer technologies that will be and strategies that will be developed over the coming few years. We had 2 years ago when we started, we had hoped to have a regular international meeting where like-minded individuals and organizations would get together and brainstorm, and these would be great conferences and networking opportunities. But the coronavirus has forced us to change our plans, and so our main vehicle for communication now is through this webinar series, as well as our website. And so these, as Milka just pointed out, these are all recorded. They're on our website for posterity, and I encourage you to look at these if you haven't seen some in the past. And we have a program for the coming year, so provide any feedback in the questionnaire if there are topics that you would like to see. One development I would like to point out in the last year is this initiative called CASH, which stands for Critical Assessment of Computational Hit Finding Experiments. It's a public benchmarking competition to rank, to systematically rank computational methods for ligand discovery. It's modeled on the CASP initiative that was instrumental in developing protein structure prediction methods computationally, and which was the vehicle that AlphaFold and Rosetta Fold, which are now super successful, but they use the CASP competition to develop their technologies with groups in the PDB and the protein structure field. And now we think the same could be done for protein small molecule computational prediction. And so this is a program co-organized by Aled Edwards and colleagues and Mathieu Shapira, with the goal of helping the computational community benchmark their tools and drive the de novo computational identification of small molecules binding to proteins. So stay tuned for that over the next year. It will be launched, we hope, the first competition in the spring. And on the website, there is you can sign up if you're a computational biologist want to participate. We're bringing on new partners to help us organize ourselves, and you'll hear a talk from members of the Juggling organization today, and other groups such as several European and global consortia, such as the SGC, UB Open, Resolute, FAIR Plus for FAIR Principles of Data Dissemination, UB Open Screen, NIH. Several NIH projects have embraced the Target 2035 principles and goals, and many individual academic groups. So we're excited about having these organizations join the effort and embrace the principles and help us go forward. And so if you would like to get involved, here's some suggestions of how to join in the program. And I will end by saying thank you for joining, and I share Milka's enthusiasm for the great talks and discussions we're going to have today. Thank you.
Thanks, Cheryl. I think we have actually a quick moment for one question, and that's the question that's probably on everybody's mind. Can new organizations join Target 2035, and how can they do it?
There's not a formal process. It's get in touch with us. Bring your ideas for what you want to do towards this goal. And we can, the existing groups that I mentioned can, there may be opportunities to collaborate. If you have infrastructure, particularly organizational infrastructure or technologies that you want, particularly technologies that could be benchmarked. So many of these consortia have, platforms that could potentially test out new technologies. So those are some of the ideas, but there's not a, there's not a membership fee or anything at the moment, or any legal signing up. It's more just a collaborative, let's do this together, and we decide what can be done together. One thing we are working towards on the SGC website is to try to host, we have to figure out how to do it, but we want to host what I would call a collaboration marketplace, where people with different ideas and expertise and technologies can find others with complementary expertise and capabilities because this is such an interdisciplinary area, to find the right match where we can help each other. Yeah.
Thank you. Thank you, Cheryl. Hang in there and we'll come back to the panel Q&A at the end. So it is now my pleasure to introduce Thomas Landrin, who is with Just One Giant Lab, which I don't know anything about and I'm curious about. Seems like a fascinating open source science sharing place. So Thomas, why don't you tell us what you've been up to?
For sure, with great pleasure. Hi, everyone. So my name is Thomas Landrin. I'm based in Paris. Thank you so much for the invitation, and we're so glad to be partnering with Target 2035. It's such an exciting venture into open science. So I'm just going to share my screen very fast to give you a small presentation to introduce you to the concept behind Just One Giant Lab. Just One Giant Lab is a non-profit organization based in Paris, but it operates worldwide. And it was created quite recently, about 3 years ago. And the goal really is to provide an infrastructure to develop what we call community-driven science and innovation. It's a new modus operandi to enable easier collaboration and transfer of knowledge and assets when you want to do open science and open source innovation. And so in terms of contextualization here, we live a very special moment, what we could call the age of communities, even though communities have already been existing since a very early age of humanity. But thanks to the internet, it takes a whole new level, and so you can just interact and work and collaborate with anybody in the world. And so to create communities of interest, of knowledge, around like a specific problem, it becomes so much easier. And so of course science is going to be impacted here, except that when you look at institutions, academic institutions, or even like large companies, they're not made to interact with communities. It's very hard for them to have this kind of very agile flux. It's so we saw that we need to create a new kind of interface to enable professionals working within institutions and also in between institutions, and also individuals who are not part of those institutions, like independent scientists, makers, and all students, to be able actually to work more easily together. we also have this new revelation of open laboratories. So now you can have access to actually quite good pieces of equipment in non-institutional setting, such as in Fab Labs or community biolabs. So it's opening up a lot of new perspectives in terms of creating scientific endeavors and also common interest innovation. But we need to solve one main issue, which is, how do we bring, people, and how do we liberate capacity to take initiatives? Because as professional researchers, you've been all through the bottleneck of when you have an idea, it takes a certain amount of time to be able actually to put that idea into practice, because you need sometimes to ask permission, to receive funds, to find collaborators, etc., etc. What if you actually could do that extremely fast? And so that's the whole idea here. Is you don't have to wait if you want to find collaborators, people who would be interested in collaborate with you. You can do that. If you want to find resources, assets, and all, likewise. And so we are trying to bring, let's say, project leaders, could be researchers, entrepreneurs, civil servants, even activists, with contributors who can be students, professionals, patients, citizens, and all. And so under which, it's just one giant lab somehow represents a new kind of institution. So it's a bit contradictory here, but it's the idea is, how do we create that kind of framework where you feel like you're able to work efficiently with people who will not normally be your typical collaborators, but where you feel like you have the same trust relationship. So we've built, in the last couple of years, we launched the digital platform during the summer 2019, so about 6 months before the pandemic hit. And really, COVID-19 has been for us like a huge growth phase, because back in February 2020, we launched the Open COVID-19 initiative. We became one of the only places on the web where people could gather and collaborate on the creation of open source solutions or open science projects around COVID. And so here is just a map. We have about almost 7,000 people on the platform nowadays, more than 400 projects. And really what has been amazing is to see how the project dynamics, like how fast people could come together, make proposal. We partner with foundations and public institutions to receive funding and resources that we could actually provide projects with. And the projects were also evaluated directly by the community. So we initiated a new kind of open evaluation framework where the due diligence of project is done by the community itself, which really put the community at the center of all the setup here. And so what came out of this, I'm not going to talk too much about it, because I'd like to go also to Target 2075, is out of more than 150 projects, about 40 of them got selected by the community for their potential impact and feasibility. And we only provided a very small amount of money, what we call macro grants, to them, up to 5,000 euros, but it was just enough for them to make proof of concepts. And a project who had good results, could ask many more times. And so we, out of just a budget of macro grants of 120,000 euros, we got 10 scientific papers to be published in peer-reviewed journals, and more than 20 functional solutions. So it was really impressive in terms of yield, of efficacy, and so now we're actually trying to bring this modus operandi to the help of other initiatives and communities around the world. So it's a very highly interdisciplinary community also, and so it's very easy to find people who would be complementary to you. The people joining Juggling usually are here because they are ready actually to help, or to be collaborate with other people. We all share the same motives, to do open science and open source innovation. And so at the end, Juggling is really like this non-profit open source digital infrastructure for communities to thrive. So now I'm just going to change screen so that I can show you how it looks like on the Juggling platform. There we go. So here I am on the Juggling platform. So you can join on app.juggling.io, and here I am on the Target 2035 space. Here you will be able to find all the basic information about what is the Target 2035 project initiative, and also about its activities, members, projects, and all. And so if you go to explore here, for example, if you go to explore here, you go to spaces, you'll be able actually to find Target 2035 here. And so what's nice is, so you can look at the members of the community. You can browse through it, so you can see the affiliation, the skills, interests. You can actually go, Susan, I'm going to take you as an example here. So you can look at potential skills. You can follow that person, for example. Here are some other links here for social media, but you can have a look to the message that she sent before. You can have more information about Suzanne here, and you can also have a look to the portfolio of Suzanne, like kind of projects or communities she's part of. So it enables you actually to be able to also learn more about someone or be inspired by what that person is doing. And when you go to a project. So here, in the case of Cash, it's more of a call for project here. You'll be able to find it also on the Target 2035 space. But it's let me show you maybe what a typical project will look like. So if we go to projects here. So you can just browse through the project. You can use keywords if you want to. I'm just going to, so this is by the most recent project. So I guess let's use this as a filter to see which one have been reviewed positively by the community. And yes, so I'm just going to use this one. No, that's this one, sorry, because I wanted to show you how you can use needs. Okay, so I'm just going to use this one. So here's a typical page for a project with this abstract. Who is the leader of the project? It could be several people. You can actually look at the team here. Who is behind the project? You can click on the profile again. And here you have a small description of the project. So here, this is an ongoing project. And you can see that this is actually participating to a specific challenge. You can have a look to the challenge here. But what I wanted to show is as a project, you can also share specific needs. Like that project is looking for people with specific set of skills, for example. And so if you're an individual and you're looking at just helping out, you can just actually go to needs and look for specific skills that you have and browse through the needs of the existing needs that project have expressed. Yeah, so this the idea is to this is an still a beta version platform, so we're still evolving very fast. We are going to implement also the community peer review soon within the platform, so you'll be able actually to call upon your community to review projects directly within the platform. And yeah, would love actually to hear from you guys, what your experience is, if there are specific things you'd like to see be implemented. And I guess that's it. We are extremely glad to be partnering with Target 2035. Again, it's we also believe that this can really be the current of the open genome sequencing project that we got back in 20 years ago. So thank you, and I'm looking forward to see you using Juggling.
Thank you, Thomas. And stay online for the Q&A at the end of the entire session. Now we will transition to Paul Workman and Albert Antolin, who are joining us to tell us about some updates to the chemical probes portal that have happened over the last year and a half. So Paul and Anton, please, Albert, sorry, take.
Thank you, Milka. Can you see my screen okay?
Yes, we can.
Okay, and can you see my laser pointer?
Yep.
Great, all right. So thank you for the introduction, Milka. Great to be part of this excellent movement, as it were, and excellent webinar today. I want to say something to avoid confusion right at the very beginning. So the Chemical Probes portal does not make or supply probes. Please don't send us your order or your credit card or request whatever. We are a web resource that provides recommendations on probes to use for researchers to use, advice, guidelines, and information. Of course, we work, in our academic labs, we make probes and we collaborate with others, but the portal itself is an information resource. So I want to start with the acknowledgements, and I want to acknowledge in particular this fantastic portal team shown here with their roles. They're all based now at the portal is based at the ICR. It remains, of course, independent. It's an independent, non-profit resource. So we have PIs, academics collaborating, as you can see, where many of these people come from internationally. And we also have, on the Welcome Grant that we won to support the portal, we have some of the people shown here that do much of the important work. And so this afternoon, I will give an introduction and just summarize what we do and the changes that we've made. And then Albert will give a live demo on the portal. And I want to acknowledge also our Board of Governors with the outstanding chairship of Milka. And we had a meeting together with the portal team and the Board of Governors very recently. It was fantastic. Got lots of advice and feedback, and we greatly value their oversight of and input into what we do. We are a resource for the community, and so we want feedback from the community about the job that we're doing. These are my standard disclosures. So I used this recently, and people were quite amused by this quote. It's a quote that goes back several hundred years. I think it might have originated in Germany, and it says, "It's a poor workman who blames his tools." So we all have to take responsibility for the research tools that we use, whether it be an antibody or a clone or a chemical probe. But both probe experts and non-experts need help with this. And we are hopefully one of the solutions to that need. There may be some newcomers to chemical probes, so I'm just going to have one slide that really exemplifies why having high quality chemical probes are important and why not using low quality flawed compounds is important. This is the story on one slide of the PARP inhibitor that never was. Here is a researcher that maybe doesn't know too much about probes, but they have, the reviewer 3 has asked them to do an experiment with a PARP inhibitor to get the paper published, or for whatever reason, right? So the researcher goes to the computer, looks at previous literature, looks at online search engines, and looks at compound vendors. At one of those actually at many of those compound vendors, you will find this compound. It's called inaparib. You can buy it, it's quite cheap, no problem with getting hold of it. And note that it's described as being a PARP1 inhibitor, number one, with demonstrated effectiveness in triple negative breast cancer, and refers to a phase 3 trial. So it must be good, right? You can buy it, it's got a chemical structure, and it's effective in patients. But all of that is wrong. Here's the paper published 2017 that shows that inaprib non-selectively binds histone, promiscuously binds cysteine-containing proteins. Here's the evidence that shows it doesn't inhibit PARP. Here's the evidence that it does chemically react with all the proteins on that gel. And here's the results of the phase 3 trial that shows that it was inactive in the phase 3 trial. This compound was poorly characterized in the original papers. Its structure, very clearly to anybody who knows chemistry, shows the likelihood of metabolic toxicity, reactivity, promiscuity. It's not a bona fide PARP inhibitor. It's inactive in phase 3 clinical trials. It actually risked the derailing of the whole PARP field for a while. It's still sold by vendors. It's wasting time and resources. I rest my case. And this is expensive, right? You can quickly look over this. It's on our website. It shows that based on some calculations, billions of dollars are being wasted by the use of worthless compounds of the type that I just showed you as chemical probes. So what does the community need? It needs to increase the number of high quality chemical probes across the proteome, and that's the job of Target 2035. Also needs to increase the understanding across the research community about the selection and best practice quality use of probes. So this is a twin need here. They're both essential. You need the science. You need the probes to be made, tested, and shown to be good. But you need to communicate across all the user communities, many biologists, hundreds of thousands of biologists, for example, around the world, who would not know that inaprib is a highly reactive, worthless compound. And that's how we get widespread best practice around the world, and we increase robustness of research. So one way, I'm not going to go into this in detail because we've talked about this before at other webinars, but one way to help with this is to provide guidelines. So here's a paper that Ian Collins and I published with what we call fitness factors. Here's the criteria that were developed by the SGC, and that the portal uses both of these in our assessments. This is the original paper led by Cheryl and Aled, with many of us as co-authors, that created the portal in 2015, indicating that guidelines were not sufficient, but you need a resource like the portal to help with the communication problem. I don't know whether you can see this. It's slightly obscured by the Zoom stuff at the top of my screen, but this is, you can see the choir here with Whoopi Goldberg singing. This is preaching to the choir. You can make all these recommendations. You can publish them in Nature Chemical Biology and elsewhere, but biologists don't read those. So we need to find other ways to get information on high quality probes and best practice use out to biologists. So this is published. So I'm just going to highlight that Albert Bissan and I published a report in Future Medicinal Chemistry that highlighted how resources could be used to help with this problem. So for example, you have the literature space with Kemble and PEB. You have the various initiatives, some of which you'll hear about this afternoon, that are creating chemical probes and making them available collectively, that published or unpublished, that creates the collective knowledge space. And from that, you can then have expert review analysis and recommendation. And that's what the portal does. You can also have computational data-driven analysis, and we and others, we with ProbeMiner and others, for example, Probes and Drugs and Small Molecule Suite, provide the second approach. Used together, these are very powerful. This is way too complicated, but it'll be available, and I'll send it the review to if you need. It's a decision tree to how to get to a high quality chemical probe. First of all, you look to see if there's an expert curated resource like the portal. Then you also look at whether there's a computational resource. And then you can go through the decision tree about what to do about your particular need. And Cayman published, took the information and displayed it in this quite easy to read way, and it's on their website here. You can take a look at that. Cayman and Chemical Probes will get you to a poster with this on it. So you must choose wisely. This is the Grail Knight in the Indiana Jones movie. We all know what happened if you make a bad choice. You come to a sticky end. So what have we been doing over the last 18 months to 2 years? a completely new infrastructure, both front end and back end have been rebuilt by the developers, greatly improved, and integrated functionality, easier to maintain, to update, and to modify going forward in the future. Better user experience, we hope, getting feedback that says we are achieving that for visitors and for reviewers of the probes. Unified chemical database, robust compound registration pipeline. Lots of technical stuff here, includes the things listed here. We now have nearly 400 probes. We only had a handful of probes in 2015. We've doubled this in the time that we've been running the portal, and have ambitious aims to obviously to meet 2035 targets. We have the historical probes, which you shouldn't use, but advice on those. The probes are peer reviewed with info provided. Albert will show this. They've been reviewed either through journals or through the donated chemical probes that Susanna will tell you about. Then they're reviewed by our scientific expert review panel. And this panel has been refreshed and increased to 184 members. We need more, by the way. We have multiple classes of action. We have information center with all the information listed here. We have news and blogs. We are on portal and Twitter and LinkedIn. And the use, as mentioned, the use of the portal is complemented by the quantitative resources. Just a little bit of detail. Here's the protein families covered. Obviously, we need to broaden the breadth of the dark proteome, as Cheryl referred to it. You know, it's a little bit dominated by kinases and epigenetic targets and GPCRs because that's the way the science was hot. But we need to broaden it. And these are the different classes. That's what I meant by classes of compounds. For example, we've brought in PROTACs and we have 20 of them on the portal. These are the interesting, you might think this is interesting to see, the most viewed probes in 2021. This is a not particularly high quality in terms of its characteristics, but it's a glutathione peroxidase 4 inhibitor, and it's involved in ferroptosis. I think it's hot because of that. A couple of degraders, a couple of bromodomain compounds are hot. One a degrader and one an inhibitor. A couple of a new class of inhibitors, an RNA methyl transferase inhibitor. A couple of lysine methyl transferase inhibitors. The RAS 12 G12C inhibitor and an improved P38 inhibitor. As I said, communication and outreach is absolutely critical. So what are we doing there? We're speaking at lots of conferences. We are both virtual and, when we could, live. We are doing these webinars, including this one, multiple publications coming out. For example, Suzanne's paper that she'll probably highlight, a Nature Communications Q&A that Cheryl and I have done with one of the editors of that journal, and a Nature Reviews Methods primer that we've been asked to produce. We've had detailed discussions with the Nature Journal editors leading to those things. They've produced a checklist that they will use internally based on the type of thinking that we and colleagues have produced. We have lots of news coming out, and we're on social media. So the new website is now live. The old website has been left alive. If you really insist on using it, you can, but it will soon close. Here's the new shiny portal with its bow. Please do use it if you haven't used it already. Please follow us on Twitter and LinkedIn. Please do submit probes on our much easier and nice to use system. Do also contact us if you're interested in becoming a member of the expert review panel. The rate limiting step is going to be, as Target 2035 ramps up and we have more and more probes to review, is going to be just like at the journals, getting people to review, provide high quality reviews. So that's crucial. So thank you for listening so far, and over to Albert for the live demo. I'll stop sharing my screen, Albert.
Yeah, thank you, Paul. So can you all see my screen? Can you see my screen?
Yes. Yes.
Yep. Yeah,
okay,
we can, Albert.
Sorry.
Yeah.
Sorry. So thank you very much, Paul, and thank you all. So it's a pleasure to show you the new website and the new portal that we've been developing over the past years. So as Paul mentioned, we have a completely new interface, both front end and back end, with a completely new database that makes it so much faster and easier to get the information. And this is the landing page. So we have maintained a bit the structure of the landing page to make users still recognize the portal. So the central area is this search box, Google style, where you can search for probes or your targets of interest. Then we have these quick navigation buttons where you can browse, for example, or go to the information center. And then we have some news that we regularly update. Just to show you very briefly the basic functionalities, of course, you can browse, you can order by targets, for example, and filter those targets. And you can very quickly see the cell rating and in vivo rating. Another area that we've been working on very early is the information center. Again, one of our aims is to convey this information to the community to help people understand better how to use and assess chemical probes. So we have this useful information on the types of classical chemical probes and the important properties they need to be aware in order to judge or assess or choose the best chemical probes, like activity, the importance of using control compounds, measuring of target activities or target engagement in cells. We've also done this for PROTACs, and as you can see, the criteria are somewhat similar, but they are also different, not covering some particularities of PROTACs, like the importance of measuring DC50, for example. And similarly, we've also developed the same for molecular glues and molecular glue degraders. Again, a similar idea, but some specific tailored to this specific class, like measuring this with mass spectrometry or proteomics. We also have a section on activity-based probes, although for now we are not capturing or assessing activity-based probes in the portal. And we've very recently developed a new set of guidelines for using and developing probes for use in animals. And again, please read those. We've developed them with a lot of care, and they highlight some of the important things, like, for example, it's very important to measure the plasma exposure and the plasma free fraction. That's not always done. As Paul mentioned, we also have historical compounds. These are probes that we don't recommend, that were historically useful, but are now not the best thing you can do to study specific targets. And we have tutorials that we plan to keep increasing. We also have a people section, and you saw this already, but we are very thankful both to our board of governors and the scientific experts that provide their time to assess probes, and that's really at the core of the portal. And I'll just if we go back to the landing page, I'll just demo very quickly, in the interest of time, a very simple example. So for example, you can search for specific probes, but probably what makes more sense is search for specific targets. So if you search, for example, for the kinase ABL1, this provides a nice example. So you see 4 probes that are annotated against ABL1 in the portal. And you can see imatinib, that's probably the one that comes to mind to most people, the most famous ABL1 inhibitor. It comes up 4th with only 1 star. So you can click view to check more information. And again, the nice thing of the portal is that apart from the rating, we have the expert review comments, and they very quickly point you that imatinib has inadequate selectivity to be used to study specifically ABL1 kinase. So again, very quickly and very clear. If we go back, for example, at what's the probe that comes up first is asciminib. So if you are not familiar with this chemical compound, you can check, and you can see that it was assessed by 3 reviewers. All they gave them top scoring. And again, like the information, very useful of the comments of the experts tell you that this is an allosteric inhibitor, that it's more than 100-fold more potent than the previous version of this compound, and that has exquisite selectivity for ABL kinase. That's why it gets a top scoring. And also very interesting, showing the importance of these reviewer comments. So you can see their experience of using and testing this compound in the lab. So this reviewer tested this compound in their lab and found activity at 2 nanomolar concentration. So we take the recommendation on concentrations very seriously, because as you all know, it's as important as using the right chemical probe, or the best chemical probe to study a target is to use it at the right concentration. So you can see things like this in the portal. where, for example, this illustrates that there's been debates between the reviewers on what's the top concentration that can be used, and we've amended this accordingly, and now we recommend this probe for concentrations up to 1 micromolar in cells. Again, in the left-hand side, as you used to have in the old portal, you have the references, some vendors. You also have the primary data on this probe, for example, the in vitro validation, no? The KD was in that range, for example, for ABA1. Also the EC50 or EC50 in cells, no? 0.25 nanomolar, and also selectivity and other criteria. So again, this is how we normally envisage that people will use the portal to try to find the best chemical probes for their target. And very quickly, I just wanted to show you very quickly that the also thing that we've been working, again, empowered by the underlying databases and the use of CANSAR, is on submitting probes and making the portal more user-friendly for the community. Sorry, let me make this smaller. So again, if you wanted to submit a probe, for example, this one, and everybody that's registered in the portal can submit probes. So before you had to introduce all the chemical details, et cetera. But now, if you want to submit a probe that is in the underlying database, but just searching by name, if you find it, you can just select it, and all the chemical information is already uploaded. So you don't have to enter this manually. Again, this makes the process so much easier. Very similar if you want to introduce control compounds or orthogonal probes, and also for the target. So if you want to introduce, for example, that the target for this probe is ATR, again, you just have to select it from the list and save it. And the target information is there with all the cross references to all the resources, all the names, etc. So you would then normally, with these yellow things, we highlight the thing that we encourage you to submit. So here you would have to edit and add the mechanism of action, IC50, etc. And if you scroll down, also the selectivity. So I won't do this in the interest of time, but just to show you that now it's much more easy, much more user-friendly to submit probes to the portal. So we encourage you to submit probes. Please check the criteria that we use to make sure that you submit high-quality probes. And please use the portal. Please spread the word. This is free. This is to use. This is, as Paul mentioned, a resource made for the community. So please join us in trying to reducing the lack of reproducibility and robustness of biomedical research by using top chemical probes. Thank you so much.
Thanks, Albert and Paul. We'll actually reserve questions for later so that we can go through a very ambitious agenda today. I think the bottom line takeaways from this presentation is that Chemical Probes Portal needs the community support. So if you could do the following 3 things: volunteer to be an expert reviewer, if you wish so, submit your compounds for evaluation and inclusion into Chemical Probes Portal, and then spread the word about this resource to your especially non-chemical biology friends who need to use valuable chemical tools to advance their research. Those would be the 3 main takeaways. So get in touch with Paul or Albert if you have any questions on any of these 3 things.
Milka, could I just, sorry to interrupt, could I just say one thing, which is in terms of submission, it doesn't have to be your probe. You might have seen a great compound in the literature and say, that really should be on the portal. So you can recommend somebody else's compound too.
Perfect, thank you. So we are staying in this space of probes and drugs and moving on to our next speaker, Stibor Škuta, who joins us from the Czech Open Screen initiative, and he will be telling us a little bit more about the Probes and Drugs portal, as well as what they've been up to at Open Screen.
Hello, everyone. Thank you, Milka, for the introduction, and also thanks Target 2035 for this opportunity to be here with you today, and also be in the company of such a great speakers today. First, I will start with a short introduction to the history of the Probes and Drugs portal and why we actually created it. Well, in the year 2015, actually shortly after the initial version of the Chemical Probes portal was created and released, we were standing in front of the task of a large update of our bioactive compound library. And we didn't want to buy any pre-compiled library of bioactive compounds, but we wanted to do this selection ourselves. And for that, we did our research, and we found out that to get all the necessary data, especially all the compound sets and all the data that are associated with them, it's really hard because they are very scattered all over the internet in different larger or smaller focus databases, different web pages, publications, and their supplementary informations, and also the vendor sets, because we needed those to actually know what we can buy. So in the end, our goal was to put all of the relevant sets somehow together, and then also to provide a user interface, like some kind of a tool that would allow anyone to work with the set and analyze it. And then after a few months of work, we actually found out that this tool can be also useful to other users, to the community. So, and then in year 2017, we released the portal and we also published it. And at the time, the portal had around 30,000 compounds representing 29 compound sets. The situation now is a little bit different. Currently, we have 76 compound sets. And I will tell you how does the probes and drugs portal work. So at the beginning, we have all the compound sets that we have to put together. These are of different types, because also not only chemical probes compound sets are interesting, of course, but also drugs and other sets. For example, from the chemical probe sets, we integrate compounds from the chemical probes portal. We have 2 sets from the SGC. We have also like the computational set from the probe miner, also the set from OpenMe, and we are also harvesting and extracting the data from high quality papers. But then we have also other sets, these like non-commercial ones that will help us with the description of the compounds and with the enrichment of our library. And for example, we have a full database from Drug Bank or Drug Central. We have 2 really high quality sets, like full database from Guide to Pharmacology. And also we extract the information from the concise Guide to Pharmacology, which is like this biennial series of publications published actually also by the UFRBPS. These are both great resources. And apart from these, we also, for example, harvest data about problematic compounds. So we have the historic compounds from the chemical probes portal, but we, for example, also we have this set from the paper about the nuisance compounds in cellular assays. So you will actually get some kind of alerts at our resource. So, and when we have all these sets together and we upload them to the database, during the upload, all the compounds undergo some kind of structure standardization. So they are better like matched together. We strip the salts, we strip the solvents. We also, for example, normalize some functional groups. And during the upload, we also, based on their structures, we also match them to our databases to get as much data about the compounds as we can get. So we get the data from Campbell, Guide to Pharmacology, and other resources. And then probes and drugs, using this database that we just created, provides a set of tools that allows everyone to work with the set. Mainly, it provides a really powerful and I would say pretty intuitive filtering system that is enhanced by Boolean expressions and also structure-based queries. We provide various visualizations that you can use for your currently filtered compound set. We have a lot of external links for all the data that we harvest into our resource, but also to other resources. And we also devised our own probes and drugs probe likeness score, but we also integrate other scores from chemical probes portal, like the ratings that you heard about, but also score from the probe miner. And at the end, if you want to export something, you can do it into Excel or CSV, or with each new version of the probes and drugs portal, you can actually download the full database of all the data that we have, and you can work with it at your local PC if needed. So this is the current state of the probes and drugs portal. Currently, we have around 84,000 compounds, and from that 30,000 drugs. These include approved drugs, experimental drugs, or withdrawn drugs. You can, of course, filter just for the approved ones. And we have also more than 4,500 chemical probes. We classify these probes into 2 different categories at the probes and drugs portal. And these are first the experimental probes. And these are like the compounds that were published that are compounds like published from the probe characterization experiments. So very often they are extensively profiled, the data are consistent. You will also get, for example, the control compound for these probes. And then we have the calculated probes. These are like in silico evaluated compounds using some kind of combination of a public data and some kind of a scoring function. So you say, okay, based on our function, we took the data, for example, from Campbell, and it seems that this compound could be a probe because it seems that it's potent and it's selective. And we call these compounds calculated probes. And these are the sets currently from ProbeMiner, and also one set extracted from a paper about the tool compound set. What you see here is the main workspace of the Probes and Drugs portal. Here in this part of the workspace is the current compounds that you are actually working with. At the beginning, when you enter the workspace, you are always starting with the full database. That means 84,000 compounds, and then using the tools that are here from my point of view, on the left. There are tools that you can actually use to work with the set. There are different tabs. This is the main tab where you can actually use all the filters and combine them, but then you have also some kind of focused tabs where you can, which are focused, for example, on some probe criteria, on compound sets, on structural alerts, and others. And then you can use these various visualizations. I will show you them. I will show you to them in a minute. And the main part is here, the filters, which I will also describe now in a minute. So first, there's the representation of a compound. You can see you get a lot of iconic information about the attributes of the compound, whether it is a probe or not, or approved drug, whether it is available. It means whether you can actually buy it, because it could be a deal breaker for you if you find a good compound and it is not available to buy anywhere. You will get a probe likeness score, some basic physical-chemical properties, and some information based on the context of the probes and drugs. For example, a number of compounds with the same scaffold as the compound you are looking at, or a number of compounds so that the compound is a member of. Then I already told you that we integrate also the probe scores from different sources. So here you can see the probe likeness score for one of the compounds, but you can see also the ProbeMiner score. These two scores are target-based, so you will get different score for each compound target combination. These are for the MAPK10 target. And we also have the ratings from the Chemical Probes portal, and these are, of course, overall scores of the compound. And we have to normalize these scores into the same scale. It means 0 to 100%, so you can somehow compare them when you are working with the portal. And the last, probably the most important part of this workspace is the target section, where you get the information about all the associated targets, the potencies in biochemical and cell-based assays, associated pathways, mechanism of actions. You can also get to the references, and also like to reveal all the associated pathways with the target. These pathways are from the reactome. And this is our filtering system. What you can see here are actually 3 filters that are changed together through the Boolean expressions. And this simple query is stating that you are looking for compounds from the Chemical Probes portal, currently 401. These are only the probes, not the historic compounds. These are in a different set. You want these compounds to have at least 10 associated targets, and you want them to be dissimilar to imatinib. So that means like the intersection, and difference. The whole set from the whole database is top-down filtered here. You can see number of compounds at the input of each of the filters. And here you can see like the result at the end. You get 72 compounds for this query. You can easily switch between the Boolean operators, drag and drop the filters, or even use brackets, and run pretty complex queries. And for the compounds that you filter, you can also use various visualizations, for example, cluster heat maps, chemical space, Venn diagrams, or even distributions of physical chemical properties, and you can even compare different filtered sets. Each compound also has its compound detail view, where you can get even like much more detailed data for each of the compounds. You are looking at just this part of the compound detail view. And this is one of the chemical probes. So for this compound, you will also get several probe related sections. The main one is the probe info here, where you will get the main attributes. This is calculated, but also experimental probe, and it's PND approved. I will tell you what that means. And you will also get all the scores. And for the probes and drugs score, you will get the partial scores from which you will get the final PND probe likeness score. There are 7 partial scores in the PND probe likeness score, and they are also based on the most common chemical probe criteria that are used for chemical probes. Potency in biochemical assays, selectivity, potency in cell-based assays, on target potency, then some synergy score for these 3 because they are really important, and then binary scores for control compounds, orthogonal probe, and structural alerts. And the PND probe likeness score is the sum of all these partial scores. It is a number from 0 to 100%, and if you reach the threshold 70%, we label the compound as PND approved. And currently we have more than 1,100 such probes. Other probe related sections are the controls or control, if it's available. The orthogonal probes, that means probes with different chemotypes for the same target. They are ordered by our probe likeness score. And of course, also similar probes. That means structurally similar probes for the same target. Using all these data that we have at the probes and drugs, this year we published very, I would say, comprehensive and comparative overview of all the sources that we have in our database, the chemical structures underneath, and also targets and target families. We've also compared different scoring schemes in this paper. And based on this study, we also established something we called high quality chemical probes, which is a live probes and drugs compound set that is updated with each new version of the probes and drugs. And it currently contains more than 600 compounds and covering almost 500 distinct primary targets. If you want to know more about this study, you can read it here in the paper called "Will the Chemical Probes Please Stand Up?" That's almost all for me. I would just like to thank to our director and probably the most active user of the portal. And I would like to thank him mainly for his endless support, to Tomáš Miller for his technical support, Martin Popper for his help with the acquisition of the compound sets, and also our collaborator, Christopher Sudden, who will be actually the next speaker. It is great to collaborate with him, and he also provides us with a very thorough feedback for the portal. So that's all for me. Thank you for the attention.
Thank you, Tibor. Thank you very much. We will come back to you with questions at the end of the webinar. And for now, if you can start. Yes. Thank you. We'll move on to our next speaker, who actually was just introduced. So I will hand it over to Christopher Sutton and let him tell you more about his thoughts on resources for chemical probes. We can't hear you at the moment.
Okay.
Now it's better.
Right.
Yes.
Right, and the slides are up?
Slides
Brilliant.
are up.
Okay. Good. Thanks very much for the invitation, and also pleasant to get a little honourable mention from Tibor. Okay, let me go straight in because time is short. I'm going to present curating probes. Just as a bit of context, I was on the curatorial team for the Guide to Pharmacology for about 5 years. I've pleased to recently join Medicines Discovery Catapult, who are helping support academic drug discovery in the UK. A lot of information on their website. They do have a strong interest in chemical biology. I shall float the idea of engagement with Probes 2035 when I get back. I'm also honored to be on one of the 184 on the expert review panel. So what I need to do now is good. Okay. Yes, we're pleased to have our latest effort in the NAR database issue for the Edinburgh team. This is their 8th. Personally, it's my 5th since 2014. The origins of the current guide to pharmacology are back in the IUFAR. I'll define that later. Database back in 2009, which evolved into the Guide to Pharmacology database 2012. So the team and the associates and the management have a record of artisanal curation way back to the first issues of GRAC, Guide to Receptors and Guide to Receptors and Channels, as BJP publications back in 2004. Coming straight up to date, we have now latest release 11,000 ligands, nearly 9,000 chemical structures, mapped or curated to just over 1,500 proteins with annotated quantitative ligand interactions. These are curated from about 7,500 papers, and we have a few patent-only entries. Some of these have surfaced on the on Binding DB, but they're interesting because they're sometimes the first surfacing of target to ligand interactions. We manage 6 releases a year and put a PubChem submission in straight away. And as Sibor kindly mentioned, we do have these concise guide 2-year publications in collaboration with the BPS and BJP. And we also pioneered with BJP the live outlinks for inside the manuscripts to the papers. So what does Guide to Pharmacology choose to curate? It's kind of a balance between the strategists of the funders of the supporting them and the Nomenclature and Standards Committee of the International Union of Basic and Clinical Pharmacology, commonly shortened to NCIUFAR. And they're unique for the database as much as it has almost a kind of a super curator level of about 100 target class subcommittees of roughly at least 800 active scientists who certainly help with updates in the particularly before the concise guides. So we have a historical focus on lead compounds, clinical development candidates, and approved drugs of human diseases. Typically, we'll take 1 lead per paper, but also they'll annotate secondary target interaction data if it's captured. We have a focus on new targets for sure, in terms of opening up new areas of pharmacology and, by definition, expansion of the druggable genome. We have a definite interest in probe publications, but in terms of the current constraints of database operation, it's not prioritized for complete coverage. So we also focus on the quality of publications. So we don't have a total capture mandate, and we exert flexible judgment. For example, you'd accept a lower potency, maybe even micromolar, for the first ligand sets against a new target. Okay, so this is simply comparing the Venn diagram of 3 sets. I got the probes and drugs, all probes, which you just heard about, and I've just introduced you to the current content of Guide to Pharmacology, 8,400, and this is what Sibor told you about his high quality probe set of 620. So kind of a selected set. Most of these are experimental probes, I think. So you can see that we've captured in total we've captured nearly 550 probes, and roughly half split between the high quality set and some of the other probe types, including probe miner, etc. So if you do these Venns, the segments are downloadable, and you can cross map them onto P&D, Guide to Pharmacology, or PubChem. So this is it's a fun thing when you're doing cheminformatics. You get this round tripping issue, which is whatever way you do the analysis, the numbers are never exactly the same. There are all sorts of technical reasons for this, some which are quite important. But just to say, if I do it by the Inchi keys or by the PubMed IDs, it's slightly different. So I have here displayed the 301 guide to pharmacology CIDs that intersect with that set of 620. These are you can sort these any way you like. These in fact ranked by date, and just draw your attention to some of the real power of being a PubChem is you can do practically infinite slicing and dicing. You've got 240 sources and loads of filters and selects you can combine and compare and contrast. Just as a simple overview here, you can see here these are actually custom filters of mine. Quite a high match to compounds extracted from patents. Doesn't actually tell the IP status of those, but it's kind of overlooked sometimes. This tells us that actually 2 of these entries in PubChem have come only from the Guide to Pharmacology. So we were the first to extract the paper. This is lead light filter, and a lot of them in binding DB where they may hit the patent extractions. The bioassays here are not a little bit short on 301. Most of these should be coming from Kemble, but they may come from other types of assays. So there's a little bit of a shortfall. Interesting enough, quite a few of these have got PDB matches, and the vendor intersect here is actually quite high. Okay. But with all the many, just about 60 million vendors in PubChem, there's a certain caveat emptor in what you sign over your credit card for. An example of an entry from the Guide to Pharmacology. This one is the Bayer 6672, and the Bayer team published a nice publication in JMed Chem. So it's selective prostanoid receptor antagonist. So here's the detail, and this is the commentary. This is the, if you like, expert commentary from most of these recent ones are from my ex-colleague Elena Facenda, who curates. And in this case, you can see we're the only entry in PubChem that makes a direct link to the PubMed entry. So that's PubMed to PubChem reciprocity. It's not obvious in the new design PubMed, which actually lost some of the functionality, unfortunately, but you can find it's down at the bottom as a cross-reference to compounds and substances. So this is the basic annotation you get. You can find interesting things under these Inchi key callouts. For example, you can hit Unichem and see you'll see patent matches from Shaw Kemble and other sources. So this is also annotation in the biological activity field of the Guide to Pharmacology. So it's interesting. If you should, I would recommend anyone who's interested in working in a probe should follow up the PubChem entry. They certainly for the very popular probes, it's not always for the faint-hearted. There's a certain overkill in information in the records, but there's a lot of stuff there that you can find out. In this case, it's always intriguing to see who else has submitted this particular probe. Now, in this case, we've got 5 other entries. First one in here was Shaw Kemble from the patent, although it was some years later before they extracted it, but there's no name on it. So we were second in back in last year, and we've put the name in. Once again, there's this issue with the hyphens, that the hyphens have to be permutated without hyphens as well. And since then, you've got a couple of the suppliers are pitching in. This most recent one is also from Kemble. I don't think it was a literature extraction. It was it was an entry that the SGC put in. And you can see these patent identifiers to track back to the patent. But this issue of choosing a control, I mean, it was a good paper from the buyer group in that JMed Chem, but it leaves you, you can't actually select a control very easily, because you actually had 60 SMILES rows in the supplementary data sheet, 180 compounds in the paper. And if you look at the Tanimoto neighborhood in PubChem, mostly patent extractions, it's 220. And amazingly enough, credit to Bayer, they've actually published nearly 300 IC50s in this patent. But the low potency compound they put in their paper, this one, which would be quite nice, up a few orders of magnitude less than the probe, it didn't get into PubChem. And just as a bonus, you can see a deuterated compound in the extracted from the patent, but probably wasn't made. Complementarity across the sources, GTOP, so curation from leads, curators' comments, manually annotated cross pointers, and we submit to PubChem in the PubMed with PubMed reciprocal linkages. If we have new targets, they will eventually go into our SwissBot cross references. So it's a kind of a verification of the papers. Probes and drugs, I won't need to go through this because you've already heard it from Seaball, but it's good to see these unique pre-computed intersects with other sets. We have a collaborative kind of a data exchange with Guide to Pharmacology. They will occasionally extract a review article, whereas the Guide to Pharmacology does not, and they'll pick up our releases very quickly. Kemble, SAR extraction with bioassay submission. It's a probe minder source, and it'll take that to some SGC direct submissions. Binding DB, SAR extractions from papers and from full extraction sets from US patents. They'll go into PubChem. So you are welcome to send your best probe papers to Guide to Pharmacology, but obviously whether they can triage it or not will depend on the curatorial capacity for that release cycle. Challenges. I think we know some of these. Some publications are not completely fair. You might not get the SMILE strings or the IUPACs to easily extract the chemistry from the paper. It would be nice to get every probe into PubChem and the targets into bioassay. From Seaball's full set, about 50 are not in PubChem at the moment. So there's other cross-screening data to generate, which to move into databases. And as it's been alluded to, the availability, the identity of low activity controls remains problematic for a lot of the probes. So this was interesting. If you saw this recent paper from Lee and Shapira saying a council, it is actually correctly spelled, Council of Perfection, where they're recommending this quartet of the two chemotypes and two controls. Although Seaball pointed out you could navigate towards this in probes and drugs already. Now it's just a plea. I think it's spitting into the wind, but wouldn't it be nice if people standardize their code names just to 3 letters and a set of figures? As I say, hyphens complicate things, and they generate threefold redundancy. And as Paul has pointed out, there is a lack of warning flags in databases for these obsolete and problematic probes. The implications of the 80% patent matches is not entirely clear. You will find SAR sets on a good day, but we don't know what IP constraints there may be. I think that we could enhance the probe to target IgG coupling, possibly through Pharos as one of the sources, as their flagship source for the IgG. Now, Guide to Pharmacology could certainly increase their focus on curating probes and probes candidates, including cross-pointing to control compounds, but they would need funding for this to do. Last slide, a few papers. Seaball's kindly mentioned this. It was very, very nice to be invited to join them and this RSC MedChem special issue. This is an older paper we got out, kind of describing the trials and tribulations of curating. Yeah, and it's a guide. If you write a paper, it'll tell you what's towards making things curatable. Okay, and this is something more recent on the wider issue of connecting documents and structures. And I'll put my slides up on Vendo, and there's a few connections there for you, a few instances if you want. So that's it. Thank you very much.
Thank you. If I understand, you have to dial off, actually.
I'm afraid so. Yes. Do forgive me,
Okay.
but we'll catch up later. Okay.
No problem. So
Bye. Okay.
if any questions arise, please contact Christopher directly.
Okay. Cheerio.
Thank you. So now we are moving to our next set of speakers, which who are Florian Montel and Marcus Köster. They're both from Boehringer Ingelheim, and they will tell us about this basically open resource for the community that they have been developing. So Florian and Marcus, if you guys, yep, we see your slides.
Do you see the slide? I just need, can you hear us?
We
Yes.
can hear you guys as well. Thank you.
Super well. Cool. Thank you so much, Milka, for the introduction. Thank you, everybody, also to give us the opportunity to attend to this monthly webinar of Target 2035 and to have the chance to present openme.com. We will try to do our best to succeed to Adrian Carter, that you probably know quite well as originator of OpenMe, as originator of 2030, Target 2035, but also recently, until quite soon, the sponsor of openme.com. So we thank him for this. So let me start by the introduction of openme.com. So this is a Boehringer Ingelheim open innovation platform. So it means that you can reach out to openme.com by just typing openme.com in your browser on any tablets, laptop, computer, smartphone, and even watches. And you will end up into this landing page here with a beautiful carousel of small vials of compound. So these resources are available to anybody without any registration. We have three main pillars on this website. You can find the molecule to order that I will introduce in a minute to you, which are named M2O for us. And these are compounds, tool compound that we provide free of charge without any discussion about intellectual property. So you will go there and I will show you how to access to this compound in a minute. Marcus will give you an introduction on the molecule for collaboration, which invites scientists to submit a research proposal to use our unique molecular probe. We will not touch today the Open2 expert, but you can also have a look at this resource. This is a place where we put some very precisely formulated biological questions, but this is not the topic of today, and we will skip this pillar. Let's start with molecule to order. So as I mentioned, these are really probe compounds developed by Boehringer Ingelheim in the last years, where you can have just access to the entire data set and the compound. And in few clicks, you will put them into your shopping cart, and in few days, you will get them for free on your bench. So we have today 67 molecules to order, and we have now shipped more than, I think, 5,000 compounds in more than 50 countries. Let me just give you a little bit of kind of flavor of what we can offer on the website. So we do not offer here a huge collection of compounds like you have seen just before with the former colleagues, but we offer extremely highly characterized probe compound developed at Boehringer Ingelheim mainly and covering a large range of proteins, so different type of proteins. You can see in the middle, for instance, nuclear receptors or ionic channel modulator. We have, of course, a lot of kinase inhibitor, but we touch really all type of proteins like GPCR or epigenetic target, for instance. We have also frame in red PROTAC molecules. We have 5 and more to come in the future in collaboration with the University of Dundee, that the University of Dundee and the lab of Alessio Ciulli accepted nicely to share on OpenMe. Some of these compounds have been developed within a collaboration between the University of Dundee and Boehringer Ingelheim. So as I mentioned, you can go to the website. You have access to the entire data package with in vitro, in vivo data, sometimes selectivity, toxicology, everything which is available on our side. Some of these compounds have been pushed quite far, even in human. And after 5 clicks, this compound will end up into your shopping cart. And in a few days, you will get them on your bench without any discussion. You just have to click a disclaimer that you will not misuse this compound, and then you can do whatever you want. You will get 5 milligrams in the first shipment. And of course, we are very happy to provide you more of this compound if it's needed for your in vivo experiment. But then here, for ethical reasons, we need to understand a little bit more what we are doing, what you are doing. But it's not mandatory to tell us more details, just to understand the species and the goal of the experiment. We don't need to know what you want to prove and what you want to test. Let me just show you a little bit the flow and to show you how easy it is to get this kind of compounds. You end up on the landing page where you have this carousel. You select the compound of interest, for instance, here the SOS1 inhibitor. You click, and then you have access to the page of the compound, our SOS1 inhibitor VBI1. And you see quite a lot of information at the top, 3D structure, co-crystal structure with the protein if we have access to this information. You can download the entire profile as a PDF. And then below, you have all the different type of category of information you may want to see. In vitro activity, in vitro DMPK and CMC parameters. You have access for most of our compound to the negative control, selectivity data provided by a collaboration with Eurofin, and again, if available, the co-crystal structure. All of this is available for free without any discussions with us. Why do we do that? We do this because we would like to increase the quality of the science and the interaction between academic world, biotech, and big pharma. It has a real huge consequence on the daily work of colleagues in academia to test their hypotheses. Today, OpenMe has generated more than 60 independent publications, and I am very clear, BI did not participate in most of this paper. We are just aware of the publication just when the paper is ready for submission or for publication with the editors. So we do not control any of this publication, but we were very happy to see that this paper were published thanks to the sharing of our molecule. I would like maybe to highlight here 1 or 2 papers. So for instance, this one in Nature Cancer from the team of Van der Eyden about our FAS inhibitor, or this beautiful paper in Nature last year about the way that the team managed to decipher the mode of action of our BCL6 degrader, finding a completely new mode of action and showing that our compound is a molecular glue. So we are very happy of all of this, and of course we are extremely happy to continue to support you by providing free molecules. You can always reach out to the team with the contact us formula that you can see on the web page. If you cannot find your target, we may have a project somewhere in our archive, and we may have a tool compound also for you. With this, I give over to Marcus for the molecule for collaboration.
Many thanks, Florian, and I hope you can hear me just as well as you can hear Florian. So thanks also from my end for inviting me today to present actually the second pillar of OpenMe, which is our Molecules for Collaboration program. It kind of complements what we do with our Molecules to Order program in a way that also here, certain molecules are in the center of quests that we actually, with a clear objective in mind, share with the scientific community to harness actually its full potential outside of the premises, well, outside of the remit of Boehringer Ingelheim initially. The program actually started also as the Molecules to Order program 4 years ago. It's amazing. In November, we turned 4 already. It's been quite an amazing journey. And just as of today, we have just recently offered our 10th molecule on OpenMe, and that has led to more than 800 proposals, which resulted into more than 50 partnerships with academia, biotechs mainly. So what has been basically our objective when we actually launched this program? Here in the center is really kind of that we are kind of interested in a certain mechanism. And I would probably say is that in terms of identifying its full potential, there are internal questions. And we then consciously select basically then this molecule to share it outside. We call this kind of a selective revealing process. And by this allowing independent scientific groups to come up with novel scientific hypotheses and propose them to us, to our panel of scientific jury. And well, upon selection, then these scientific ideas are pursued together as part of a bilateral scientific collaboration. So this has turned out to be very nicely and successfully. And as you can see here from the 10 projects that we shared, we actually covered different modalities and even different phases during product lifecycle as well. So we actually started originally with small molecules, but in the meantime, with the example, say, for instance, of the IL-1RAP monoclonal antibody, we also managed to share here large molecules and proteins, monoclonal antibodies, and also we managed to share actually a molecule. Thank you, Florian. You know, so novel modalities such as an adeno-associated viral vector, which we shared actually already in 2019 as well. So I just mentioned the most recent one has been just recently being completed, which is our dual venin inhibitor that we just launched, actually offered until end of November. And I think if you go to the next slide, Florian, you will see that this has actually first of all, again, another example from our discovery research pipeline. We actually offered for a very short period of time this potent and selective dual venin inhibitor with a goal to unravel human disease mechanisms with this tool. We knew, or we know that this is also well described, that the venin enzymes regulate cellular redox homeostasis, and they are functionally implied in oxidative stress regulation and inflammatory processes. And of course, the question is now, well, what does this inspire scientists outside of Boehringer Ingelheim to use this compound for to test elsewhere? And this is further kind of incentivized that we also offer monetary funding to those scientists with the best proposals that are then pursued together. I just mentioned the deadline has just recently expired, just basically 2 weeks ago, and this has led to 47 proposals from 21 countries in total. Again, a very nice outcome, and we are actually very thankful for all scientists across the world who have actually joined this challenge. So it's actually a nice outcome again, and we have now just started the evaluation phase, which will probably extend until end of January next year, and then we look forward to work with the winners. So on the next slide, it kind of summarizes once more, basically the success that we have achieved with OpenMe in the 4 years so far. We have now more than 3,000 registered portal users from more than 60 countries. We have more than 1,000, almost 1,400 individual molecules to order orders. Actually, it's actually something I should probably point out here in the context of this audience here, that the vast majority of them are actually ordered with a negative control. Again, highlighting how important it is to biologists to educate them that the usage of negative controls is actually highly beneficial to validate the biologic findings that they actually obtain with our probes. I've already mentioned the more than 1,000 research collaboration proposals. You know, still most of them come from our Molecules for Collaboration program, simply that launched 4 years ago, while our Open to Expert program that we're not addressing today has only been launched beginning of last year. So overall, we are actually very thankful for this great reception in the scientific community. And yeah, looking forward to entering another exciting year next year, where we hope to launch more exciting molecules to orders. And actually, I can share with you already the next molecule for collaboration project is already in the pipeline, and I'm looking forward to launching that also in the first quarter next year. Thank you so much for giving us that opportunity.
Thank you very much for sharing. This has been a very successful initiative on your part and opened a lot of collaborations, it seems. So it's wonderful to see it.
Thank you so much.
So we'll move on to our last speaker for today, and then circle back to Q&As at the end. So we have Suzanne Müller-Knapp, who will be sharing with us what Structural Genomics Consortium has been up to recently. Suzanne, please feel free to share.
Okay, thank you very much, Milka, for the introduction, and I'm very happy that I can present here the SGC Chemical Probe Program. Okay. So I guess many here know the SGC, that we are a public-private partnership. We receive funding from many different sources, which are depicted here in the bottom of the slide. And we are currently about 150 scientists based on sites in Toronto, Frankfurt, Chapel Hill, McGill at the Karolinska Institute, and at UCL. Everyone, I guess, also knows that SGC is a strong advert of open science, and we place our results, reactions, and know-how in the public domain, and that sometimes requires quite a bit of effort. Our main outputs are high throughput structural biology from the beginning. We have a small effort on antibodies. We generate and test compounds in patient cell-derived assays, but the main focus is on chemical probes and chemogenomic libraries, and that's what I will talk about today. What are chemical probes? I think the criteria have already been introduced by Paul and also by Tibor. These were the criteria that were generated or established by the SGC early when we started with the epigenetic probe program, so 100 nanomolar biochemical potency, 1 micromolar cellular activity, and 30-fold selectivity within the family. We want to see target engagement, and there are certain criteria that we want to see for the compounds in terms of stability, solubility. We want that these compounds are available in terms of physical compounds, but also the data. We want to have an inactive control to the compounds, and they should have no pain elements. Contrary to Paul, all our data on the compounds are available, and you can order them simply on the SGC website. There's a very simple click MTA that you basically don't feed the compounds to anyone to cause harm or something like that. And we also share our compounds with commercial vendors, because after all, we are not vendors. We just make the compounds available in the interim until someone picks them up. But we have distributed probe samples quite successfully. So we have more than 20,000 probe samples distributed, 10,000 probably from the donated probe program and 10,000 from the other programs. And our probes are highly cited in more than 10,000 publications. But how do we ensure the quality, the high quality of our compounds? So we have every probe compound evaluated by 2 independent committees. So we first generate something that we call a probe proposal, where we include all information on the probe. We also put this compound in perspective in terms of what other inhibitors are available for this target. Then this probe package is proposed to our joint management committee, which consists of representatives of the pharmaceutical industry and also academia. If that is approved, it will be then further evaluated by the Chemical Probe Scientific Committee, which are independent academic reviewers, and they will make the final decision if this probe is accepted in its current package. Then it will be approved. Otherwise, then the package may be rejected, or they will request revisions, in which case we can repropose the proposal until the compound or the package fulfills the requirements. So these are the current chemical probes without the kinase probes, which are not depicted here. So these are the epigenetic probes. you've seen we've been very successful in terms of the, covering bromodomains and also methyl transferases. We have been less successful, not for lack of effort, on the lysine demethylases, and there have also been very few selective methyl lysine reader probes. The successful programs in terms of the bromodomains and the methyl transferases have been published in 2 very nice articles where all data are again assembled in one place and not distributed in different places, and all data are also for the individual probes on the website. So some things that we learned was that our probe criteria are not always sufficient. For example, for bromodomains, here depicted is a profile for a pan-bromodomain inhibitor, bromosporin. And here is the bromodomain profile for the BET inhibitor JQ1. And as you see, bromosporin also hits several other bromodomains. But if you look in a transcriptomic profile at the 1,000 most significantly differentially expressed genes in 2 different cell lines, you see that the profiles of the pan-bromodomain inhibitor bromosporin and JQ1 are literally identical. So that also means if you inhibit any of the BET bromodomain family members, you will have such a dominant phenotype that it doesn't matter if you inhibit any of the others. This is also shown in a kind of a different way here, where we generated a selective inhibitor for CBP EP300 bromodomains. And you can easily see in this Gleason correlation that if you increase the dose of the compound, that it picks up more and more of a BET profile. So confirming, which I think everyone knows already, that it is important to have the right dose of an inhibitor. And this is also why we at the SGC always recommend a dose range or a dose limit for our compounds. We also found out, not surprisingly, that compounds can have unspecific effects. And one specific example is shown here when we developed the histone lysine demethylase inhibitor, where we transfected either the wild type or catalytically dead mutant protein into cells and looked for the corresponding histone mark, which is reconstituted upon addition of the inhibitor. We saw that sometimes even the mutant protein gave a kind of a spike in terms of the lysine histone mark. But when we looked closer at the cells, we saw that this was associated with cell death. We then tested unrelated compounds, here in this case doxorubicin and paclitaxel, which for sure are not lysine demethylase inhibitors. And we saw that when cells are dying, they do change their chromatin methylation state. And so this is the reason why we now also for our current programs, we assess the compound effect on cells, and I will come back to that. So what are we currently focusing on? We focus on several different families on kinases. The epigenetic is continuing, but with less effort. One of the main efforts is currently on increasing the number of E3 handles. We work on WD proteins, mainly in Torontos, and on SLCs. As you can imagine, with these large families, kinases with more than 500 members, E3 more than 600 members, this is something that the SGC cannot really work on its own. So in the program UB Open, we have assembled a really nice effort with other organizations, University of Dundee, Oxford, ETH in Zurich, Fraunhofer Institute, EMBL, and so on, because only this way I think we will be able to succeed in develop inhibitors for these large families. I now would like to highlight a special program which is really close to my heart. It's currently run by Claudia Twedo. So this is the donated chemical program, which has been initiated by 7 pharma partners associated with the SGC. But as you can see here from the contributors at the bottom, it has gained interest from other companies as well. And we have now a very nice probe set of 97 approved probes. And contrary to SGC probes, many of these probes are also suitable for in vivo use. They have been highly developed in the pharma companies, and they have been given the physical compounds as well as the associated data to the SGC, so we can make them available to the community, because we can do this often much easier than the companies do, although Boehringer has just shown that they can do this as well. I would like to encourage people who are on call here or who see this video afterwards to contribute their high quality compounds. They will go through the same kind of evaluation process that I highlighted in the beginning. And we would love to hear from you for your compounds. We then make all the data available. First of all, in a human readable format, so that everyone can have a look if this, for example, selectivity criteria has been reached, or which are the closest off targets, and you can easily click through this. But we also make the data available in a fair format, so they are findable, accessible, interoperable, and reusable. And we've uploaded our data, as already mentioned, to Campbell, so that they are also available and easily mineable from there. This program has been, not surprisingly, very successful. So we have different libraries. We have the whole library, and we have shipped about more than 90 of the whole libraries since 2018. With more than 10,000 single compounds that have been shared to 90 organizations in 26 countries. But now with the number of probes that we have, we can also create subfamilies. So you can order a kind of kinase set, a GPCR set, or a protease set. We now make the synthetic routes also available to certain vendors. So we currently collaborate with Sigma, Tokros, and Cayman. And the uptake is now starting there as well. So already 37 of the probes and 10 of the negative controls are also commercially available. So if you need more of the compound and we can only supply a limited amount, you can get a larger amount from the vendors. We make sure that we have regular quality controls of the stock solution, so that we send you compounds that are ship-shape, they are not precipitated. And we also developed a high content assay so that we can give you some kind of biological QC for the compounds. So on the one hand, and this is about to be published soon, on the one hand, with the Hooks channel alone, we can give you information if the compound has precipitated or has a tendency to precipitate, if there's any fluorescence associated with the compound which may interfere with your assay. We then look further at the healthy cells to see if compounds induce apoptosis, or if cells are just mitotic, because that's not easily distinguished by just looking at the pycnosed nuclei. We give you information if a compound causes alteration in the cytoskeleton, if there is an increased mitochondrial mass, or if it permealizes the cell membrane. And we've also set up a Fuji assay to give you information if the compounds have any effect on cell cycle. So then if you take these compounds, and this is done in these 3 cell lines, U2S, MRC9, which is a fibroblast cell line, and HEC293 T cells, and you test them in your specific cell line, you have already an underlying data set, and you can compare with that and see if the observed effect in your specific system is different or the same as we have already annotated here. I want to switch gear now a little bit, just 2 more slides on chemogenomic compounds set. So this is a rather new concept that we work on. So if you look at chemical probes, there is a kind of a 1-to-1 ratio of compound to target. Whereas if you look at the chemogenomic compound set, you really need a kind of a set to link the observed phenotype to a target, because each chemogenomic compound, although it's very well annotated in terms of selectivity and cellular on-target effect, you hit several targets and you may need an overlapping set of compounds to really deconvolute the phenotype you are seeing. We have established chemogenomic criteria for chemogenomics compounds according to family, and they're all posted on the UB Open website. The first chemogenomic set has been released by the UNC site and has now been recently extended. So there are 188 inhibitors targeting 211 kinases in the first set, and that has been expanded now to 403 inhibitors targeting 262 kinases. And that set is available through the UNC website. And I omitted to add the web link here, which I can add later, or someone can put in the chat, please. And this is now the first set. And within UB Open, we want to establish chemogenomic sets for a third of the druggable proteome, covering 1,000 targets by 2025. And then being by kind of the basis for the target 2035 goal, hopefully. In the framework, we established also kinome-wide selectivity assessment in cells, because if you look here, the biochemical selectivity of a kinase inhibitor can differ quite substantially from that observed in the cells. And Lena and Benny have been working on this and can now access more than 200 kinases in this live cell assay. With that, I just want to highlight the different S3C libraries that are available. The slides are available on Target 2035, so I won't go through this, just mentioning they are displayed here so you can access them. And with that, yes, I won't go into detail here, just highlight a few groups. So this is the cellular assay set here in Frankfurt, the team here in Frankfurt working at the donated probe team under Claudia, partners in the donated probe set, people at the University of Oxford working on the bromo domain, all the different people at the different S3C site, UNC, Toronto, Karolinska, people at the ICR we collaborate with, all our pharma funder and the whole S3C team, because for sure I have forgotten a lot of people. Thank you for your attention.
Thanks, Suzanne. It really takes a village to accomplish all this. So what I would like to do now is invite all the speakers to turn back their cameras on so we can properly thank them for really giving us a lot of information and a lot to think about and a lot of resources to consider using. I will give everybody in the audience just a couple of minutes to think about questions. We have one for Suzanne, so we'll start from there and see where we end up. So from Mark Wade, Suzanne, do any of the SGC activities and collaborations in the E3 ligase space involve proteomics?
Yes, most definitely. And I think this has been inspired also by the work of the Chemical Probes portal, where we defined for the first time more specific criteria for evaluating degraders and what is a good degrader. So it's now also part of the S3C criteria, and I think also publications, that a good E3, a good PROTAC has to be evaluated by proteomics.
Yeah, and if I can make a big plug for Dana-Farber and what we're trying to do in this space, Eric Fisher has recently made public our effort basically to profile at no cost to the ProTech or a molecular glue creator their compound in a chemoproteomics experiments. So that effort is led by Catherine Donovan in Eric Fisher's group. And we are making our chemoproteomics platform available to people. And in return, we will keep the data, we will share the data with the group and have a 6-month embargo at which the group can do whatever they want with their chemoproteomics data. And after that 6-month period, we will make the data public. So you can learn more about it, and I will drop the link in the chat. Again, one more effort to make this sort of data on degraders more complete and publicly available. So any other questions? And remember, panelists, you can just unmute yourselves and ask.
I just want to say how wonderful that is, Catherine Donovan and the Fisher Lab, to provide that resource. It'll be really, really useful. Yeah.
Thank you. So I'm just trying to find the link. Any other questions or comments?
I could make a comment, Milka, following on from what you said, which is I also think it's great of Eric and Cheryl's comment. One of the things that's been coming up quite a bit recently in talks I've been giving in various places where we talk about the very high stringent criteria for the top quality chemical probe. This came up talking to, for example, Terry Shepard at Nature Chemical Biology at papers he sees, came up in lots of conversations I have with early career researchers. So these are people, as you know well, starting out with small groups, maybe a chemical group, or and they get really spooked by us. I think everybody agrees that promiscuous compounds just need to not be around. But the problem is, how do you get something published, or how do you get the first compounds out there that might start with an early career group that doesn't have the resources to do proteomics, that can't do a kinome screen? And I think there's two things. One is, if you collaborate, that's a way to often to get stuff done and still keep some control of the publication of your own probe. Secondly, there is no problem publishing. I've forgotten who said it. I think it was Chris Southern. In an area where a probe has never been made, you can publish a micromolar compound. Just don't call it a chemical probe. Otherwise, everybody in Cell, Nature, and every journal will be using it, even in animals, before you know where you are, right? So it's about, we used to call them in our chemistry and biology paper, which you edited, the review, Milka, we used to call them pathfinder compounds. We still do. These are pathfinder compounds or prototype probes. Right. And as long as you say what you've done and say, look, we've only done 5 kinases, somebody needs to do 500. That's okay. Right. And those papers should be published. It just don't overclaim. And of course, there's a tendency to overclaim to get the thing published. So I think the journal editors, working together with the community, will find a way that early career researchers, for example, can publish non-optimized probes for mutual benefit.
Yeah, absolutely publishable, especially first-in-class inhibitors, even if they're weak. Very valuable to the community and generate good publications. Yeah.
But here's a problem that you get. So I used to work very heavily in PI3 kinases, and I think in 1997, the Lilly Group published the famous LY294002. This was a micromolar PI3 kinase inhibitor that was a pathway compound, first in class, inhibited class 1 compounds. Subsequently, it was shown that it inhibits bromodomains, protein kinases, and all kinds of other things. And it's only micromolar potent on the target, let alone in cells. LY is still published at 500 PubMed citations per year, and the much better compounds, I have to say, including one of ours, trickles along at a few citations per year. And that's because the problem here is biologists use the chemical probes and they publish the great stuff and also the flawed stuff, right? And so they go to PubMed or they go to the vendors and find LY. I even had a referee telling me once, why haven't you used the LY compound? Because it's the most highly cited and must be the best compound. Of course it isn't. So that's the communication to the biologist thing that we have to find a way. We're all talking to each other. I bet everybody on this call is already in the choir, and we're preaching to the converted. I hope there are people who aren't already in the choir and will join. But I think that's the problem we face. How do we get out of this bubble and find a way to talk to biologists about how to improve what is a pretty bad situation out there still?
Any other thoughts that people would like to share? Well, we are up for right at noon. Well, Eastern US time. So what remains is to thank everybody for showing up today, for sharing, inviting everybody to get in touch with our speakers and engage and continue the conversation in all these aspects of chemical probe research, development, and validation, as well as sharing. So thanks to Target 2035, I wanted to upgrade you to 2030.
Not yet, not yet.
Not yet. So thank you for hosting this webinar, and thank you for nucleating the community. Thanks everybody, and have a wonderful rest of your day.
Thank you, Milka, and all the speakers.
No,
Thank
Bye,
you,
everyone.
Milka.
Thank you.